Hey everybody, this is Larry. This is apparently a mock-up of my upcoming t-shirt if you're a fan, but just kidding, of course. Um, yeah, props to Core for kind of creating that really scary looking graphic. But anyway, today is February 11th. It is the 11th day of the February Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord where you get to see memes like this. But anyway, today's problem is routed anagrams. Okay, so usually I go over my thought process for this problem, but to be honest, for this problem, it's a little bit weird. I mean, it's not weird. It's just weird for me to try to figure out how to explain. I think for this one, it is a very common competitive thing to ask. Not necessarily directly, but usually you get asked this as part of a bigger problem, or like as a component of a problem with 3 or 4 parts or something like that, right? For a harder problem. So this is way kind of basic for competitive, and I think if you do not know how to do this, then I would urge you to pause the video and really try to figure out and work out the property of why this works. But there are a couple of ways to do this. The thing that matters is that if two words are anagrams of each other, if they contain the same characters at the same way, right? So if I had this on a competitive programming contest thing, I would probably, to be honest, solve this in about 5 seconds or 10 seconds. I'll do something like return sorted S is equal to sorted T. So that's one way to do it, because the idea here is that after we sort the characters, after we sort the characters in S and after we sort the character in T, what happens afterwards, right? What is this equal the comparison? The comparison is just character by character, right? So in a way that gets you the frequency map, and it gets it. Of course, this isn't that efficient. This is n log n, where n is the number of characters in either S or T. Of course, you would take the shorter of it because the comparison should end in a shorter version. But another cuter way of doing it is you do something like, at least this is in Python. In other languages, it may be similar, which is collections.counter of T, which in this case, it creates the frequency map into a counter, and then it just does the same thing with T. And what is a frequency map? Right? A frequency map, this just creates a hash table that looks up, that maps for each character how many times it occurs, right? So this is going to be linear time. The space is going to be O of 26 or O of 1 or O of the number of alphabets. So this is much faster, and that's the way that I would actually do it on a contest or something like that. Because it's fast, it's nice, it's fun. Yeah. And to be honest, if I was on a contest, I probably wouldn't even test this, but just because I'm very confident about it, but watch I get it wrong as a result. That would be hilarious. But yeah. So accept it. Yeah, so I don't know why today's problem is so easy, but hope let me know what you think. So this is linear time because it goes for each character and then put it into counter. So what does it? So if you're not using Python, what happens, right? You can also just think about this, expand it as kind of, okay. So we have a hash table, S hash, let's call it that, and then you have for character in S. That's what C for character. S of hash of C, increment by 1. Of course, this is not a default dictionary, so you might have to do something like, if C is in S of hash, we do this, else S of hash of C is equal to 1. And again, in different languages, in different languages, it may be a little bit different, but that's the general idea. Yeah, and then you do it again for T, and then you notice, oh, we're just doing the same thing for T, right? So actually, we can map it to a function, right? To kind of not repeat yourself. Get frequency map, and then we just have a string, and then return S of hash, and then now we can do something like, let's see. S hash is equal to get frequency map of s, t hash is equal to get frequency map of t, and then we can just do something like for each key in s of hash dot keys, we check that if s of hash of key is not equal to t hash of key, we return false, and then we have to just check one more thing, which is that if the length of s of hash is not equal to length of t of hash, then we return false, otherwise we return true. That's mostly it. You can add another thing there, but I think that should be good enough. But as you can kind of see, this is very long. Relatively, it's about 19 lines, but I think similar concept in different languages will be mostly correct. Again, now you can see why this is a linear time, linear space, linear time, constant space, because this construction is linear time, and this, even though this will only have 26 characters, or the number of characters in the alphabet, which is either 26 or sometimes it's 52 if that's uppercase, for example, or other characters, but still O of 1. So this returns an O of 1 space hash table. So we have 2 of those, and then we do a lookup. And again, keys is going to be only up to 26 characters for the alphabet. So this is a this is a constant time operation. And again, this is also constant time. So the most of the work is done here where it is linear time, right? So linear time, constant space, bam. Let me know what you think about this problem. Hit the like button, hit the subscribe button. Take care of yourself, take care of others. Do good, do well, to good health and to good mental health. I'll see you tomorrow. Bye bye. But before that, let me hey, this is Larry. Bye bye.